Hello and welcome to this free preview lecture series of my on-demand FE Electrical and Computer Exam Preparation course. In this lecture, we are going to tackle frequency and transient response of a RC circuit. Before we dive into the content, I would really appreciate if you could like this video, click the subscribe button and the bell icon if you haven't already done so. Hello and welcome to first lecture of our multi-part lecture series on the topic of frequency and transient response, in which we will discuss RC circuits. RC transient response. In the case of our RC circuit, we have a voltage source, we have a switch, a resistor, and a capacitor. So when we are studying the transient response, we are interested in what happens when the switch opens or closes. I will introduce a couple of terms and parameters that we will use in order to develop the equations and analyze the circuit. First of all, we have this circuit, which will be analyzed for time greater than 0. Okay, so the thing that's happening here, you can see it is pretty clear from the circuit that this switch is actually closing at time t equal to 0. So for time t greater than 0, this will simply look like a series RC circuit, okay, with a voltage source connected to the R and C. The initial voltage across the capacitor is denoted as VC at time 0. So the voltage across capacitor at time 0. And tau is the time constant. And I'll explain you how this time constant impacts the charging and discharging of the capacitor. For now, just remember that tau is equal to RC. So we can change the value of this time constant by selecting different resistor or a different capacitor. And V is the applied voltage. Okay, so V is the applied voltage, external voltage source that we have applied to this RC circuit. The voltage across capacitor as a function of time can be calculated using this equation. And we will understand this equation, what it actually means and represents. Let us look at a simple scenario where the initial voltage across capacitor VC0 is equal to 0. So if this is equal to 0, then this first term becomes 0. Okay, and we are simply left with this term. Now, if we were to look at this circuit physically, when the switch closes at t is equal to 0, then we have this type of a setup where the voltage source is connected to the resistor and the capacitor in the series arrangement. Okay, and remember the voltage across the capacitor initially was equal to 0. So what happens is that this voltage source will now start charging this capacitor. Okay, now a charge will start building up on this capacitor, and this equation, V times 1 minus e to the power of minus t divided by RC, is the equation that tells us how the capacitor is being charged. Now we can derive this equation very easily because we know that Q is equal to CV, and dQ by dt, which is basically current, rate of change of charge with respect to time, will become C times dV divided by dt. And we can use a differential equation in order to, it will become a differential equation and we can solve that differential equation. Now we don't have to do that. This formula is already provided to you in NCSFE reference handbook. You don't even need to memorize it. But just remember that this portion of the equation is actually representing the capacitor being charged. Now, the capacitor, let's say it starts at 0, and this is the voltage that is applied across the capacitor. Now, there are many ways that this capacitor can charge. Okay, it can charge linearly, it can charge exponentially, it can charge in many different ways. So you can see that in this particular case, it is being charged in 1 minus e raised to power minus t divided by RC format, and we'll see what that implies. So what I want you to understand is that this equation actually comprises of two components. One is the initial charge, and the second one is the applied charge across the capacitor. So if the initial charge is equal to 0, then the capacitor will charge due to the voltage source on the basis of this equation. Now this is how the capacitor will actually charge, and this is where the time constant tau is equal to RC comes into play. Now, as I mentioned, that we can actually change the value of this tau by changing the value of R or C, or both R and C. But if we were to take a general view of the capacitor charging, then we can say that, okay, when tau is equal to 1, okay, or tau is equal to RC, when tau is equal to RC, and remember, we are ignoring this because we're looking at a capacitor which had 0 charge. When tau is equal to RC, then this equation basically becomes V times e raised to power minus RC divided by RC, or it basically becomes V times 1 minus e raised to power minus 1. And when you calculate that, you basically find that this term represents 63.2%. Okay, so it means that in after one time constant, this capacitor will be charged. If it had no initial charge, then it would be charged up to 63.2% of the applied voltage source. Okay, and this is what we are seeing over here. So if the time is RC, one time constant, then this represents 63.2% of the applied voltage. Now, if we wait for 2 time constants, then that percentage increases to 86.5%. And so on, and up to, if we wait until 5 time constants, then the voltage across the capacitor would actually reach up to 99.3% of the applied voltage. Okay, so this is how the capacitor would charge, and you can see that this is an exponential curve, but it plateaus. It's a 1 minus exponent. Okay, and it plateaus, and after a long time, the capacitor would basically, when at time infinity, basically when you're looking at 1 minus e raised to power minus infinity, that's when this term becomes 0, and the voltage across the capacitor would basically become the voltage, the applied voltage. Okay, so this is very important to understand, and this is how time constant comes into play. And this portion of the capacitor basically shows us, this portion of the equation basically shows us how the capacitor is going to charge. Now, how about the discharge of the capacitor? The first portion actually represents how the capacitor discharges, and it is also an exponential, okay? And it is basically equal to the initial voltage across the capacitor times e raised to power minus T divided by RC. Okay, so after first time constant, after tau is equal to 1 times RC, the capacitor voltage would actually, if it's discharging, okay, you have to imagine that the capacitor is discharging through the resistor, then that would drop to 36.8% of its initial voltage. And whatever that initial voltage is, I'm calling it as VC0. Okay, so after 2 time constants, the capacitor would discharge to 13.5% of its initial voltage. And after 5 time constants, the capacitor would practically be completely discharged, and the voltage would only be 0.7% of the original voltage. Now, the interesting thing that you should note here is that at any given time, the sum of the charging and discharging is equal to 100%. Okay, so you can add these two columns, and it would always add up to 100%. I'll explain that briefly, but let's look at the discharge curve. So you can see that this is the discharge curve with the initial voltage starting at VC0. Now this VC0 can be anything. It can be equal to or very close to the applied voltage, or it can be any starting curve, any starting voltage. So after 1 time constant, your voltage has dropped to 36.8% of the initial voltage. After 2 time constants, it is just 13.5% of the initial voltage. After 3 time constant, it is just 5% of the initial voltage. Okay, so this is how the capacitor would discharge. Now, what about our equation now? So what we are saying over here is that if the capacitor has an initial charge VC0, okay, now we assume for simplicity that this was 0, right, to understand how the capacitor would simply charge. then at any given time, the voltage across the capacitor would be the sum of the discharge of this initial voltage, okay, plus the charging of the capacitor by means of the external voltage, okay. So this may or may not always be equal to 0. So if it has a certain value, then what you would do is you would analyze the circuit, evaluate what that initial voltage is, figure out what the applied voltage is after the switch is closed or opened, okay, and then plug in those values. So you have to be careful about it because these initial conditions, sometimes students get them wrong and they can cost you. You can see that they are very important because it really impacts how this equation gets set up. Now the current that will pass through this circuit will be given by this equation. So you have the applied voltage V and the initial voltage across the capacitor VC naught. So the difference of these two voltages divided by R. So if you were to visualize it, let's say that this circuit is now closed, the switch is now closed, and just when the switch closes, this is how the circuit would look like. Okay, so you have V and you have VC0 or VC naught, okay, and you have the resistor. Now you know that the current that will pass through the resistor will actually be the difference of the voltage on this terminal and this terminal. So the voltage on the positive terminal is V, the voltage on the negative terminal is VC0. So that's the difference divided by the resistor itself. So this is essentially what we're looking at, and this factor e raised to power minus t divided by RC basically takes care of the shape of the curve. Okay, now if the voltage across the capacitor initially was equal to 0, then this simply becomes V divided by R times e raised to power minus t divided by RC. Now the current, actually you'll see that the current based on this equation simply V divided by R e raised to power minus t by RC, this actually looks very similar to this the discharge curve. And the reason for that is that initially when the capacitor voltage is 0, then this delta would be the highest, okay? But as the capacitor voltage starts to build up, as VC0 increases, okay, the voltage across the capacitor actually increases as you're charging and you're pumping current onto the plates, then the difference in the numerator would actually decrease. And as time goes on, the difference would actually decrease and decrease and decrease. So that's why initially you start out at a very high current, and then over time, then when the voltage across the capacitor becomes more or less equal to the applied voltage, then there's no voltage difference across the resistor. And that's why the current passing through the resistor would actually become 0 or very close to 0. So V minus VC would actually become very close to 0. Okay, the numerator will become very close to 0, and that's what will drive down the current I of t. Okay, so it's an important concept to understand. And another thing to remember is that there is no current passing through the capacitor itself. Okay, the current that is actually appearing in the circuit is because of the charge that is being pumped onto the capacitor plates. And when we discharge the capacitor, we actually dump the current from the capacitor, from the plates. So physically, there is no current that is passing through the capacitor. It is the current that is resulting from the accumulation of charge onto the capacitor plates. And then finally, we have the voltage across the resistor, which is simply the current that is passing through the circuit times the resistor. So you simply multiply the previous equation with R, and you're left with V minus VC naught times e raised to power minus t divided by RC. Now again, the voltage across the resistor is going to drop because as the capacitor accumulates more and more charge, its voltage will increase and it will become very, very close to the applied voltage. So after 5 time constants, you can see that the voltage would be 99.3% of the applied voltage. So the voltage across resistor will actually decrease over time. So that would also follow this type of a curve. Now, what about the case when the capacitor has been charged, okay, and now we are discharging it by opening the switch? So you can see that previously, let's say we had the setup where the voltage source was charging the capacitor, okay, and this entire voltage V was applied across the capacitor. So if this voltage source were to stay in this position, if the circuit were to stay in this position with the switch closed for a very long period of time, and you know that 5 time constants was basically bringing us at about 99.3% charge. So greater than 5 time constants would actually be long enough. So that entire voltage, so capacitor voltage would be almost equal to the voltage that is applied by the voltage source. And then you have this current R, resistor R. So at time t greater than or equal to 0, the switch is opening, and this part of the circuit can then be ignored, and you simply have the capacitor and the resistor in series. Vc naught is the voltage, initial voltage across the capacitor when the switch opens, and the time constant tau is still equal to Rc, and the applied voltage, as we saw here, is equal to V. So now when the capacitor has been charged, okay, and it is only in a series arrangement with the resistor, then obviously the capacitor is going to be discharging, okay? And the discharge equation we've seen already is equal to Vc naught. If you go back to the previous slide, you will find that it is Vc naught e raised to power minus t divided by Rc. Now we are assuming that the voltage across the capacitor was more or less the same as the applied voltage, okay? If the switch was in this closed position for a long time, then practically speaking, that voltage is equal to V. So we will start at V is equal to Vc naught, and basically we'll follow this curve which represents the discharge of the capacitor. And very quickly again, your time constant tau is equal to Rc. So after 1 Rc, you will be at 36.8% of the initial charge. After 2 time constants, you will be at 13.5% of the initial voltage. And after 5 time constants, the capacitor voltage would actually be 0.7% of the original. So all the charge would have been depleted, practically speaking, it would have been depleted at after 5 time constants. Now what about the current? Current is pretty simple. So we simply divide the voltage across the capacitor, which happens to be the same voltage across a resistor at any given time, by R, and we get the current. Now I want to explain you why there is a negative sign over here. So let's ignore this part of the circuit and let's focus on these two. Okay, this is what happens when the switch is opened. So you're just simply left with the capacitor and the resistor. Now if I were to write a KCL at this point, then the KCL would basically say that, okay, at this point we have current passing through the resistor and current passing through the capacitor. Okay, so this is V. So V divided by R, and you know that the V is equal to the voltage is actually across the capacitor, and the resistor is equal to V times e raised to power minus t divided by Rc. Okay, so this is basically equal to V times e raised to power minus t divided by Rc divided by R. So this part is clear. Okay, so this part is clear. But when you look at the currents, you see that IR and IC are the only two currents that are leaving this node. Okay, so IR plus IC should be equal to 0. This is simple KCL. Okay, so that means that IR is equal to minus IC. Okay, and we've already established that that current is equal to V divided by R times e raised to power minus t divided by Rc. So this is how you come up with this particular equation. Again, in this case, what we are simply looking at is the discharge curve of the capacitor. So capacitor has been charged up to the voltage approximately V, and now when the switch opens, then the capacitor is being discharged. Previously, we were looking at the capacitor being charged. The switch was initially open and we were closing the switch, okay, and that's why we were getting that type of a curve. But in this case, the capacitor has been charged for a long time, and now it is undergoing a discharge process. Let us now take a look at an example involving RC transient circuit. So in this case, you can see that we have a transient setup because you have a switch which is closing at time t is equal to 0. You have a voltage source, you have an arrangement of resistors and a capacitor. And we are interested in finding the voltage across capacitor for time t greater than 0. So the relevant formula for this problem is VCT, the voltage across a capacitor at any given time t, is equal to VC naught, which is the initial voltage across the capacitor, times e raised to power minus t divided by tau, where tau is equal to RC, or the time constant, plus V times 1 minus e raised to power minus t divided by tau, and V is the applied voltage. Now you can see that initially the switch is open. When the switch is open, you can actually ignore this part, and you have the circuit in the form of 3 branches. So this branch only contains a 250 ohm resistor. This branch contains a 250 ohm as well as a 500 ohm resistor, in addition to a battery 9 volt voltage source. And the third branch is comprised of just the capacitor. So another important thing to note here is that the voltage across the capacitor is basically the same voltage that appears across this 250 ohm resistor, right? So you can see that these nodes are actually the same, or alternatively you can say that it's the same voltage that appears across this branch as well. And if this switch has been open for a long time, then you know that this capacitor will basically act as an open circuit, right? So there will be one terminal here, one terminal here. So this plate will basically respond to the voltage that is at this point, and the negative plate will basically respond to the voltage, will be equal to the voltage that is at this point. So you can essentially assume that your initial voltage VC of 0 is the voltage that appears across these two terminals, which is the same voltage that appears across the 250 ohm resistor. So building on the last explanation, if I want to find VC naught, then I simply have to calculate the voltage across the 250 ohm resistor. Okay, so we can do that very easily by using the voltage divider rule. So if I were to redraw this portion of the circuit much more cleanly and ignore this switch, ignore this capacitor, because if the switch has been open for a long time, the capacitor is just an open circuit, right? So essentially what I'm interested in finding is you have this 9 volt voltage source. It is in series with a 500 ohm resistor, which is in series with a 250 ohm resistor. So that's this branch. And all of this is actually in series with the 250 ohm resistor. Okay. And the voltage across the capacitor is basically the voltage that appears across this terminal. So VC of naught, VC naught. And you can solve it using Thevenin or simple voltage drop equation, the voltage divider equation. So I have the 9 volt battery times the resistor across which I'm interested in finding the voltage, divided by the total sum of the resistances in the denominator. And that gives me the resultant voltage, VC naught. So when the switch closes, it is important to understand how the circuit will look like. So when the switch closes, you can see that this entire portion of the circuit, which comprises of the 500 ohm resistor and the voltage source, will end up being in parallel with the short wire. So you know that when we have something in parallel with the short wire, we can actually ignore it, right? And so we can simply ignore this, and the simplified circuit will comprise of the two 250 ohm resistors in parallel with this capacitor. So when the switch closes, your equivalent resistance that will be seen by the capacitor will actually be, so the equivalent resistance that we are concerned with as far as the R is concerned is the parallel arrangement of these two resistors, 250 and 250 ohms. So 250 in parallel with 250 is 125. So the capacitor will now start discharging the current through these resistors, okay? And the capacitor's value, capacitance, is 5 microfarad. We already know that. Tau, which is the time constant, is just the product of R and C. So 5 microfarad times 125 ohms will give us 0.625 milliseconds. And when the switch closes, you can see that we don't have any external voltage source applied. So that's why V, the capital V, will be equal to 0. Okay, it's very important to understand. And that basically means that this entire term will actually disappear. So this V corresponds to the external voltage source, which is no longer present. So our Vc of t, voltage across capacitor as a function of time, will now simply be equal to Vc naught times e raised to power minus t divided by tau. And you will substitute these values in here in order to find what this answer is. So at any given time, the voltage across capacitor can simply be calculated for this given circuit by using this equation. We will now look at a problem from study guide involving a RC transient circuit. Again, in this case, we are being asked to calculate the voltage across the capacitor for time t greater than 0. One important difference in this circuit is that the switch is opening at t is equal to 0. In the previous example, the switch was closing. In this case, the switch is opening. Now, in both cases where the switch opens or switch closes, they are basically transient states, right? You're transitioning from one state to another state, and that basically impacts how the current will flow, how the voltages will change, and that's what we are going to calculate. So in this particular case, I have a little bit more extra space to work with, so I included the circuit after the switch opens so that there's no ambiguity in what we're talking about, and this is how the circuit looks like before the switch opens. Now the fundamental equation or the formula still remains the same, and we have to go through those steps that we discussed previously in order to identify what our Vc at 0, the initial voltage across the capacitor is, what the resistance is going to look like, and what our time constant is. Overall, this is a much more simpler circuit, because you can see that in this case your Vc0 is equal to 10 volts because the entire voltage source is being applied across the capacitor. So there's no confusion as to what portion of this voltage is being applied across the capacitor. Okay, so this is pretty simple and straightforward. And similarly, when the switch opens, then the only resistance that is in play over here through which the capacitor is going to be discharging is basically your resistance R, which is 10 kilo ohm. So we know our C, we know our R, we know Vc at 0, we know the time constant. Just multiply R and C and you will basically get the time constant. So in this case, as you saw, that when we open, as you can see, when we open the switch, then this becomes an open circuit. Then this voltage source is irrelevant. Okay, it will have no contribution whatsoever towards the circuit, and that's how I basically came up with this equivalent circuit. So 10 volts of voltage has been applied. Okay, the capacitor has been charged up to 10 volts by this voltage source, and that becomes our Vc0. And now these 10 volts are going to be discharged. Okay, the capacitor is going to get discharged through a discharge current into the resistor, 10 kilo ohm resistor. So when this switch opens, this voltage source disappears. So this term again, V, becomes equal to 0. We can completely ignore it, and then we can simply focus on this term. So we already established that this is 10 volts. E raised to power minus t divided by RC becomes e raised to power minus t divided by 2 because the time constant is equal to 2. So again, this is a very similar problem. All of these problems are going to be similar. They're going to have transient switch opening or closing. They will involve initial voltages. They will involve you figuring out what the value of tau is, and for you to calculate the value of tau, you have to establish what R is going to be, and so on and so forth. So you have to analyze these circuits in a stepwise manner. Don't just jump into the circuit, look at it systematically. Start with your fundamental equation. Okay, start with your fundamental equation, and then within this equation trace what your V is. Okay, your V is the forced voltage which is applied, and see what that voltage is before and after. If the switch is opening and that voltage is basically coming out of question, then this becomes 0. Okay, and similarly figure out what your R is going to be, figure out what your VC0 is going to be, and all of that will help you basically set up this equation properly so that you can calculate the voltage across the capacitor or the current passing through the circuit or the voltage across the resistor at any given time. So in both examples, we've calculated voltage across the capacitor, but you could very well look at voltage across the resistor as a function of time. You could calculate the current passing through the circuit as a function of time. We have those equations, and all of those equations basically build up on the voltage across the capacitor. In this lecture, we looked at one of the two transient circuits in detail. This is the RC transient circuit, and the other one in the context of FE electrical and computer exam is the RL transient circuit. The fact that you've gone through the transient equations, initial conditions, and the switching of the circuit and the graphs and the time constant for the RC transient circuit, it will help you a lot in understanding RL transient circuit. And these two circuits are actually quite related. The graphs are very similar. The concept with respect to the time constant and the switching and the initial conditions and the transient equations, they are very, very similar. The basic idea is that you have to be able to understand, first of all, what's being asked, what is the unknown, figure out what the initial conditions are, and impose those conditions on the transient equations. Once you go through these 2-3 steps, as we saw in the practice problems, and while figuring out the equations and looking at the graphs, analyzing the transient circuits is very easy. But if you're not able to make sense of the initial conditions, or if you're not able to really make sense of how the switching is happening and which transient equation to use, then very quickly these problems on the exam can become quite difficult, and you can actually spend a lot of time just figuring out where to start, where to begin, and what to find out. If you found this preview lecture helpful, I am confident that you will also greatly benefit from the full course that contains over 150 lectures and covers all the topics that are found in the latest NCEES FE Electrical and Computer Exam specification. You will also get access to tons of quizzes and mini exams in this course that will help you get additional practice, along with a bonus full-length computer simulated practice exam. This streamlined and well-reviewed course comes with an amazing 30-day full refund policy, no questions asked. On top of all this, I have also included a special discount link in the text section of this video.